A very good afternoon to all of you whoever joined in this second counseling session of IGNO. And the counseling session is for the course BMTC-131, which is about calculation. So now let us focus on the basic outline of this block 2 module. Here basically we have to discuss about the limit and continuity. And in this block 2, the course design are in this way. Unit 6 contains the real numbers, then Unit 7 contains about the limit, and Unit 8 is all about the continuity. So before we are going to start Unit 6, 7 and 8, there are some notations and symbolic representation before we are going to start about the real numbers. So now we are going to discuss at the beginning all about the real numbers. And as we know, set of real number R is the largest set containing all other sets like set of natural number, set of integers, set of rational number, set of irrational numbers, and all the basic operations like addition, multiplication, division, and subtraction are well known to us, which are operated by using the real numbers. And these operations are basically in the form of binary operations that were discussed in our first counseling session in the chapter of binary operation over sets. And here, throughout this chapter, we consider the set will be always set of real numbers unless it is stated otherwise. So now, let us focus on some basic definition which are new to us. These definitions and basic idea formula are known to us. They are operations of addition, that means closure under addition, and associative, competitive property, additive inverse. All these basic operations are well known to us, and these basic operations are already we are using in school level. So we are not going to elaborate all these operations once again, but we are going to focus some basic information about the set of real number, and that's new to us, which is all about the supremum and infimum. So now again, before we are going to discuss about the supremum and infimum of a subset of a real number set R, we have to know about the upper bound and lower bound of a set. So let us begin to discuss about the upper bound and lower bound of a set. So here, as you can see in the definition of upper bound, we can define like that. So we have taken here a set S. So here S be a subset of set of real number R. Then an element U in set of real number R is said to be an upper bound of S if the condition which is holds for every element X in S must be less than or equal to U. That means U must be the larger among all other elements present in the set S. So in this situation, we say that U is the upper bound of the subset S. And if this property exists, then we can say that the set have bounded above. The set S is bounded above. The condition is that if the set S must satisfy the condition of upper bound of the set S. Similarly, the same idea can be extended to define the lower bound of a set, and that can be seen in this particular definition, as you can see here now. Definition of lower bound. So here, a lower bound for a given set S for a real number V such that V is less than equal to S. That means here you can say that in simple language you can say that V is the smallest element among all other elements present inside the set X. That means all the elements present in the set X are larger than V. So in this case, you can say that V is the lower bound of the set S. Now, if this condition is satisfied, if this property holds by the set S, then we can say that the set S is bounded below, and the value of V is known as lower bound for the set S. So now let us discuss the same definition of upper bound and lower bound with the help of this definition. So here we have defined a set in the form of a set builder form, and the relation is defined like that: n plus 2 divided by n, and here n is a set of natural number n. So as n is a set of natural number, n can be started from n equal to 1, 2, 3 onwards up to infinity. So here it is an infinite set, and clearly we can say that this particular set A is a subset of set of real number R. So now whenever we choose the relation or the function given inside the set that was defined, the property used to define the set A is n plus 2 divided by n, and clearly this particular value will be less than equal to all u, and u must be set of a real number R. Here we can see that if we can see very simple algebraic operation, it can be written as 1 plus 2 by n. So when n will be 1, the very beginning of the set of natural number n, the value 1, so 2 by 1 it is 2, so 1 plus 2 is 3. So clearly you can see that value is 3, so upper bound is 3. Meaning is that every element of the set S cannot greater than the value 3. Its value must be less than or equal to the value 3. So that's why 3 is known as the upper bound. This 3 is known as upper bound of the set S. Similarly, in the other way, you can also say that again from the same expression 1 plus 2 by n, again from the same expression we can define in the form that 1 plus 2 by n. That means here if n is infinity, so 2 by infinity will be 0 and the value will be, the second value will be 1. Now we can conclude that all the elements of the set A must be larger than the element 1. That means here 1 will be act as a lower bound. 1 will be act as a lower bound of the set. So here the set which I discussed in our focus of discussion A must have the upper bound, that is 3, must have the lower bound, that is 1. So this is the very simple and easy process to discuss about the upper and lower bound of an infinite set or finite set. Now let us move towards the basic definitions of supremum and infimum of a set. So here supremum, that is also known as the least upper bound of a set, and infimum is also known as greatest lower bound of the set. So now let us begin our discussion how we can define the same infimum of a set and the supremum of a set. So for this definition, we have taken any subset S of set of real number R which is less than. So here we can say that in that way the upper bound of any subset S of R which is less than any other upper bound of S is called its supremum or least upper bound. Or in other words, we can say that if we have upper bound property of a particular subset, then there must be more than one upper bound of the same subset. but we have to choose the least among all the upper bounds, and that particular value will be known as supremum. And the property will be represented by supremum of S, and the value will be represented like that. Now further, the same idea can be extended to define the definition of infimum. So here we can say that lower bound. So infimum means greatest among all lower bounds. That means here again we have to choose the greatest value from all lower bounds of the set S. And here that will be defined in the word by infimum. And you can also say that greatest lower bound, or in very short we can represent GLB. Now let us discuss both the definition with the help of the following example. And here we have taken a set T, and that is defined in the set of real number R with the property that x square less than equal to 4. So now if we are going to expand the expression of x square less than equal to 4, we have the inequality, that is minus 2 less than equal to x less than equal to 2, minus 2 less than equal to x less than equal to 2. So clearly we can see that 2 is the upper bound of the set T, and minus 2 is the lower bound of the set T. But according to our focus point of discussion, 2 will also be considered as here the lowest among all upper bounds of the set T, and minus 2 will be the greater among all lower bounds of the set T. So that's what in very simple and simple way we can represent the infimum of the set T will be minus 2, and the supremum of the set T will be exactly 2. So in this way, we can find the supremum and infimum of a set. Now, another definition, that is whenever a set S is said to be a bounded set. So here the definition is very simple. Whenever both the property upper bound and lower bound property are exist inside a set S, then the set will be known as the bounded set. Now, mathematically we can define like that: a set S is a subset of set of real number R is bounded if it has both upper bound and lower bound property. So these are the basic definitions in set of real number which are new to us. So basically we have to focus in these two definitions mainly in this particular real number chapters, because these particular definitions are very much useful when we are going to discuss some definition of limits, continuity, and some basic theorems in the set of real number R. So now let us discuss about some particular type of functions. The first function is now absolute value function. So here absolute value function is generally represented by a pair of vertical bars. So here it can be represent also we can read as modulus of x, or in very short we can also represent mod x. But the basic rule is that the modulus of x is defined x when x itself is positive or 0. If x is itself negative, then modulus of x will define in the form of minus x. And the same has been discussed with the help of the following 3 examples, which are very familiar to us. Now, similarly, we can also discuss another more useful theorem, and this theorem says about the property of absolute value function, or the property of modulus function. Now, if a and b are any real numbers, then modulus of a, or absolute value of a, is always greater than or equal to 0. And this particular property is known as non-negativity condition. And here, modulus of a is we represent like that maximum of minus a comma a. And the same has been proved with the help of some inequality property, and the readers are advised to go through the proof of these theorems. Now, in this section, we are moving towards the definition or some useful functions which will be used later on in our discussion. Now, let us focus on the intervals on the set of real number R. So, basically, we have four different types of intervals, and these are listed in this particular table. So here it can be represented like that. That is, first cell number one, the notation A V. Look at these square brackets. These are just in the opposite direction. That means whenever we find this type of expression in the interval, the meaning is that the value A and B are not included. That means this is a set containing all the value between A and B, but not A and B itself. So that is an open interval. Now in 2, we can represent a closed interval, and in closed interval the bracket are just towards inside, towards A and towards B. So whenever we find this kind of expression, the expression is a closed interval, and we can conclude that this closed interval is a set containing all the elements x such that x is lies between the value a and b, as well as containing both the points a and b. In the figure geometrical representation, you can clearly see that black dots in A and B. So black dots in A and B means both the points are included inside the set or closed interval AB. Now the third kind of interval are half open or half closed interval, and you can also say that it is left open and right closed, because if we focus mainly in the left hand side of the expression, in the left hand side small a, the left bracket is open, so that's why it is left open and right closed. And clearly we can represent the form of a set builder form, and it is represent like that. That is a set containing all the values in the form of x, and x is lies between a and b, but containing exactly the right hand side of the element, that is v. And clearly it is visible in the geometric representation. In the right hand side, black dot in the point B, but the point A is white dot. That means the point A is not included inside the set, because it is a left open and right closed set. In the same way, we can also define the last one, that is left closed and right open set. Now we have finite interval and bounded interval. If both the endpoints in an interval are real, then that interval is called a finite interval or bound interval. Because now we are focusing to discuss about the intervals which are containing the symbol infinity. Now, whenever an interval containing the symbol like any infinity, so these are always semi-open or semi-closed intervals. So let us discuss the functions and their graphs. So here some basic functions and graphs are given. So students are advised to go through each and every function which is listed in this particular chapter, and their graphs which are plotted with the help of coordinate system. So now let us begin to discuss about the greatest integer function. So greatest integer function is generally represented by using the square bracket symbol. An integer function from set of real number r to r defined by f of x equal to square bracket x. And this kind of functions are known as greatest integer function, or it is also known as a step function. Now let us see what is the calculation procedure of that particular greatest integer function. So here closed bracket 3 equals to 3.5 square bracket is also 3 minus 3.5 square bracket, the greatest integer value will be minus 4. That means this functions always takes the first leftmost integer, nearer integer of that particular value. And clearly in minus 3.5, to the very left hand side, the nearer first integer value is minus 4. So that's why minus 4 is the answer of that particular square bracket of minus 3.5. Now, if we're going to plot the graph of this greatest integer function, the graph will be looks like steps. So that's why this function is also known as step functions. Now, polynomial function, which I already discussed in our last counseling session. Now, next function is signal function. And generally, signal function is a particular type of function which is represented by the function like x by mod x. So, these are some graphs which are given for each and every trigonometric functions discussed. And all the basic trigonometric functions like sin x, cos x, tan x, cot x, sec x, and cos x, all the graphs of trigonometric functions are given, and the students are advised to go through the graphs of trigonometric functions because these are very much essential. We are going to discuss the inverse trigonometric functions in chapter of limit and continuity. So this is a graph of modulus function or mode function or absolute value function, and in the graph you can clearly see that the figure is shifted according to the representation of +1 or -1 from the origin. In the inverse trigonometric function. So let's have a look on the domain and range of inverse trigonometric functions. So generally, as you have three trigonometric functions: sine theta, sine x, cos x, sec x, tan x, and cot x. Similarly, to define the inverse trigonometric function, we have to first ensure that all the trigonometric functions must be satisfied the property of bijective. That means the function must be one injective or onto surjective property. Then we can say that yes, we can define an inverse function over that one, and the inverse function will be represented in the form of sine inverse x. And basically, as the range you can see here, minus pi by 2 to pi by 2, and this particular range is also known as principal value because the sine x is generally is not a bijective function. But if we coincides the domain of the sine function to a set of minus pi by 2, this small interval of closed set is now known as principal branch of the sine function. And with the help of this principal branch, you can define the inverse trigonometric function sine x in the form of minus 1 by 2, minus 1 to 1, the domain set, and in the range set it is minus pi by 2 to pi by 2. And the same basic idea has been adopted to define all other trigonometric functions by using the principal branch of all other trigonometric functions. So here, as you can see, 0 to pi, in the closed interval 0 to pi is the principal branch of the cosine function x, and because of that one, we can define its inverse function. And similarly, all other intervals listed in the right hand side are known as the principal branch of the trigonometry functions, which are helpful to define the corresponding inverse trigonometry functions. Now, let us recall the definition of even function and odd function. And as you can see, an even function, a function is said to be an even function if for each and every value in its domain, the condition is satisfied. That means f of minus x is equal to f of x. If this condition is satisfied or followed by the function f, then you can say that yes, the function is an even function. And clearly, if we observe the graph which was drawn here. So in the right hand side, that means in the positive side of the x-axis, it is an increasing function. Exactly, the mirror image was drawn in the left hand side because it is an even function. But if in case of odd function, the figure will be just opposite and it would not be a mirror image. Now let us see the definition of odd function. So here this is the same figure that was discussed in odd function was drawn in case of odd function. So that was here the figure start from the just below the y, just below the x-axis from the negative side. So here the basic main definition is f of minus x is equal to minus of f of x. F of minus x is equal to minus of f of x, and then this definition satisfied, and we can say that the function is an odd function, and we ensure that this condition is satisfied for each and every value x inside the domain D. Now let us discuss about the monotonic functions. So here is monotonic functions. So let us in monotonic function we can see that definition is generally monotonic function may be increasing function and may be decreasing function. So let us know how we can define mathematically monotonically increasing function and also the monotonically decreasing function. So now to define, look at the definition. A function f defined over the domain D is said to be increasing, or we can also say that it is non-decreasing. The condition, look at the condition very carefully. Here we have taken a pair of elements from the domain of the function D, and this pair of elements are x1 and x2. The condition is that x2 is greater than x1, then which implies that the functional value of x2 is greater than or equal to functional value of the x1. If this condition is satisfied, then we can say that yes, the function is increasing or it is non-decreasing function. Now, if in case of greater than equal to symbol, if in the same property, if there is only strictly greater than sign, then the same is known as strictly increasing function. F will be strictly increasing function. Now, we'll begin to discuss about the definition of increasing and decreasing function with the help of this graph. So clearly in this graph, it is clear that the function is decreasing function. So here the graph of g, and the graph is drawn over the function x cube, and according to the definition we have taken a pair of elements x1 and x2, and clearly x2 is greater than x1, but if we are going to calculate the value, Our functional value at these 2 points, the first functional value is at the point x2 and the second functional value at the point x1. And clearly you can say that the functional value are satisfied our condition of decreasing property. So here the function f and z are said to be decreasing function or also known as non-increasing functions. Now the same has been defined in the form of mathematical way of strictly decreasing function. So here we can say that the function f defined over the domain D is said to be decreasing if a pair of elements is taken and it satisfies the condition of the less than equal to property. That means f of x2 must be less than equal to f of x1 for every pair of elements taken in the form of x2 is greater than x1. Then clearly the function is said to be a decreasing function or strictly decreasing if the inequality will be strictly less than type. So these are some basic idea about the increasing function, decreasing function, and strictly increasing and strictly decreasing functions. Now let us focus on the definition of monotonic function. So here a function defined on the domain D is said to be a monotonic function if it is either increasing or decreasing in its domain capital D. So monotonic means both may be increasing or may be decreasing in the domain of the function. Now some figures have been defined, the property of increasing and decreasing functions. And now the periodic functions which are well known to us and the graph of some periodic functions are also given. And this is a function or the graph of sawtooth function which is also known to us in function chapter. So we are not going to elaborate all these functions. So this is the summary of first unit 6, and then we are ready to discuss about the unit 7, and that is all about the limit of a function, that means how and when we are going to calculate the limit of a function. So let us see the intuitive definition of limit and formal definition of limit. Then we are going to discuss some examples with the help of this definition of limit. So here in this unit 7, it is totally dedicated to the chapter limit, and the limit will be discussed in the form of intuitive approach and in the form of a formal approach. And here, after the defining the definition of formal approach, we are now able to discuss the limit at infinity, then some basic results which are listed in the form of theorems in the limit, and finally we are moving towards exponential and logarithmic functions, and finally the chapter or the unit end with hyperbolic functions and their inverse function as well. So let us begin to discuss the intuitive definition of limit. So intuitive means the basic idea. What is the basic idea behind the definition of limit? So whenever you are going to use the word limit in mathematics, the situation is that whenever a function does not gives us a value for a particular input value, then we are searching for its approximate value for a particular input. So here we discuss the same idea. We have taken a function in the form of f of x square minus 1 divided by x minus 1. Now the function is not divided for x equal to 1, because if we are using the value of x equal to 1, the function gives us undefined value. But suppose we need the value of the function at the same point x equal to 1. So now to get this kind of value, we are using the using or we are approaching the definition of limit or the basic idea of limit. So that's why let us begin with the same. So here we have taken the value of x in the first row and the value of the function in the second row and listed in the form of 4 to 5 decimal places. And clearly you can say that when x is approaching to the value 1, the function value is approaching to the value clearly 1.99 means it is the approximate value of 2 or it is very closer or nearer to the value 2. So conclusion is that if the function directly is not defined at x equal to 1, but in our calculation we found that the value of x which is very closer to 1 is gives us some value which is 1.599 and it is very closer to the value 2. So that's why we are able to say that the function must have some value of x equal to 1, the value, the limiting value of the function will be nearer to 2. Similarly, if we approach the value of x from the right hand side, that means we are now approaching x equal to 1 from the right hand side. That means first we started our calculation from 1.1, 1.2, 1.5, 1.5, 1.01, 1.001, and similarly 1.0005 times 0 to 1, and look at the value. Value is decreasing, 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 decreasing towards approximately 2. So in both these discussions, we very much clear that the limiting value of a function is approximate value if we are approaching from the left or we are approaching from the right. Both the value will be approximately very close to each other, and this particular value will be known as the limiting value of that function at the point x equal to 1. And the same has been represented graphical in the picture, and in this picture we can clearly find that when x equal to 1, the value of the function y equal to f of x is exactly in x equal to 1, the function value is exactly 2. So this is the intuitive idea about the definition of limit, and the same idea will help us to develop the basic definition or formal definition of the limit in mathematics. So now the same will be represented like that. Limit is now represented in the form of lim, x approaches to 1 or x tends to 1. We can also say that f of x equals to 2. Meaning is that the limiting value of f at x equal to 1 is 2. And mathematically we represent like that limit x approaches to 1, f of x equal to 2. Now the same idea will be now extended in the form of formal definition in mathematics. And the formal definition is also known as epsilon delta definition in mathematics. So some other examples are given. So here all the students are advised to go through the all examples carefully for the better grip on this particular definition. So now let us discuss about the formal definition of limit. So here we can say that in general form, let us given a function f which is defined over the set of real number r to r, and it can be represented now. The limiting value of the function when x approaches to a is equals to L, and this kind of limit will be now two-sided limit because the value L can be approached from the left hand as well as from the right hand side. So that's why this limiting value or this kind of limit are also known as two-sided limit. We are approaching from right as well as we are approaching from the left hand side. So now some examples are given in the form of left hand limit and right hand limit. So here let us discuss about the left hand limit, which is generally represented capital LHL, that means left hand limit. And generally, left hand limit is represented by a minus. So whenever we find this kind of representation a minus, the simple meaning is that there is a left hand limit of the function when we are approaching to the point a from the left hand side. And the definition is x approaches to a minus f of x equals to L1. In the same way, we can also define the right hand limit abbreviated by R as L, and here we are using the plus sign. So that can be represented in the form of a plus. That means here, whenever we find a plus in limit, the meaning is that x approaches to the point a from the right hand side. So that's why this kind of limits are known as now right hand limit. And mathematically, you can represent in the following expression. And these expressions are well known to us. So let us move in towards the definition of limits. Now, the relationship between one-sided and two-sided limits. So, limit of a function exists. Let us focus on this expression. So, whenever limit of a function exists for a point x approaches to a, the meaning is that both left-hand limit as well as the right-hand limit are exist and exactly same. Only in that case you can say that yes, the limiting value of the function exists and equal to each other. So now the definition in formal approach, and the definition is here known as epsilon delta definition of limit. So here, as you can see in epsilon delta definition, we are using some notation in the form of epsilon and delta. So that's why this is known as epsilon delta definition. So here let f be a function defined at all points near to the fixed point a, and capital A be a real number. Then the expression is like that. Whenever x approaches to a, then we can express in this form. That means the difference between x and a is very small, and that will be less than small delta. And small delta here is a very small positive real number. Similarly, if x is approaches to a and they are very close to each other, then we can say that the function and the limiting value L will also be very close to each other, and their difference will be very small, and that will be represented by epsilon. And as we know, epsilon is very small positive real number. And now, according to the property of inequality, we can also express this definition in the form of x minus a, or x is lies between this open interval a minus delta to a plus delta, or also say that this is a neighborhood of the point x. Now, after the discussion of definition of limit, some examples are given, and now we are able to discuss about the definition at infinity. That means when